Lesson: Theoretical challenges in reinforcement learning applications. Reinforcement learning has emerged as a powerful paradigm within artificial intelligence, especially pertinent to applications in cyber defense. RL is predicated on the notion of agents learning optimal policies through interactions with an environment, aiming to maximize cumulative rewards. Nevertheless, the theoretical challenges associated with RL applications in cybersecurity are multifaceted and significant, demanding a nuanced understanding of both RL principles and the complex, dynamic nature of cyber threats. One primary challenge in applying RL to cyber defense is the non-stationarity of the environment. Unlike controlled environments such as games or simulations, real-world cyber environments are inherently dynamic and adversarial. Attackers constantly evolve their strategies, creating a moving target for defense mechanisms. This non-stationarity violates one of the foundational assumptions of many RL algorithms, that the environment's dynamics remain consistent over time. Consequently, an RL agent's learned policy may become obsolete as the threat landscape changes, necessitating continuous learning and adaptation. This presents a significant computational burden and raises questions about the stability and reliability of RL-based defense systems. Another theoretical challenge lies in the exploration-exploitation dilemma. Effective cyber defense requires a delicate balance between exploring new defense strategies and exploiting known, effective ones. In RL, this is often handled through techniques like epsilon-greedy policies or more sophisticated methods such as upper confidence bound. However, in the context of cybersecurity, exploration can be risky, potentially exposing the system to new vulnerabilities. For example, an RL agent exploring a novel firewall configuration might inadvertently create a security gap that an attacker can exploit. This risk of exploration underscores the need for robust safety mechanisms within RL algorithms to prevent catastrophic failures in cyber defense scenarios. The curse of dimensionality is another formidable theoretical challenge. Cyber environments are characterized by high-dimensional state and action spaces, making it computationally infeasible to represent and learn optimal policies using traditional RL techniques. For instance, the number of possible configurations for network security settings can be astronomically large, rendering tabular methods impractical. Function approximation methods, such as deep reinforcement learning, which use neural networks to approximate value functions or policies, offer a potential solution. However, DRL introduces its own set of challenges, including stability issues and the need for massive amounts of training data. Moreover, the interpretability of DRL models remains a significant concern, as the black box nature of neural networks complicates the understanding and debugging of learned policies. Temporal credit assignment is another critical theoretical issue in RL applications for cyber defense. Effective defense strategies often involve delayed rewards, where the consequences of an action may not be immediately apparent. For example, deploying a security patch may prevent an attack that would have occurred hours or days later. Traditional RL algorithms struggle with such long-term dependencies, as they rely on discount factors to weigh future rewards, which can lead to suboptimal policies if not tuned correctly. Techniques like eligibility traces and more recent advances in hierarchical RL, which decomposes tasks into subtasks with shorter temporal horizons, offer potential solutions but add complexity to the learning process. Adversarial learning poses another significant theoretical challenge. In cybersecurity, the adversary is an intelligent agent actively trying to deceive or outmaneuver the defense system. This adversarial relationship is not commonly encountered in other RL applications and requires specialized approaches. Game theory provides a useful framework for modeling such interactions, enabling the formulation of strategies that consider the actions of an adversary. However, integrating game theoretic principles with RL algorithms is non-trivial and computationally intensive. Moreover, adversarial attacks on RL algorithms themselves, such as perturbing the agent's observations to induce suboptimal behavior, represent a growing area of concern. Developing robust RL algorithms that can withstand such adversarial manipulations is an ongoing research challenge. Sample efficiency is another pertinent issue. RL algorithms typically require vast amounts of interaction data to learn effective policies. In the context of cyber defense, generating such data can be impractical or even impossible due to the high stakes involved. Simulated environments offer a partial solution, but they often fail to capture the full complexity of real-world cyber environments. Techniques like transfer learning, where knowledge gained in one domain is transferred to another, and few-shot learning, which aims to learn effective policies from minimal data, hold promise but are still in their infancy. Ensuring sample efficiency is crucial for the practical deployment of RL-based cyber defense systems. Finally, ethical considerations cannot be overlooked. The deployment of RL in cybersecurity raises questions about accountability and bias. For instance, an RL agent's decisions could inadvertently prioritize the protection of certain assets over others, reflecting implicit biases in the training data or reward structure. Additionally, the autonomous nature of RL agents complicates the assignment of responsibility in the event of a system failure or breach. Addressing these ethical concerns requires a multidisciplinary approach, integrating insights from computer science, ethics, and law to develop guidelines and frameworks for the responsible use of RL in cyber defense. In summary, while RL holds significant promise for enhancing cyber defense, its application is fraught with theoretical challenges. These include the non-stationarity of the cyber environment, the exploration-exploitation dilemma, the curse of dimensionality, temporal credit assignment, adversarial learning, sample efficiency, and ethical considerations. Addressing these challenges requires ongoing research and innovation, drawing on a diverse array of techniques and interdisciplinary insights. As the field progresses, it is essential to balance the potential benefits of RL in cyber defense with a rigorous understanding of its limitations and risks.